The cosmic microwave background, CMB radiation, stands as one of the most significant discoveries in modern cosmology, providing scientists with a powerful tool for understanding the universe's origin, structure, and evolution. This ancient light, often described as the echo of the Big Bang, permeates the entire universe and offers a direct glimpse into the conditions of the early cosmos approximately 380,000 years after its birth. Through careful measurement and analysis of this primordial radiation, cosmologists have been able to validate the Big Bang theory, constrain cosmological parameters, and solve fundamental puzzles about the universe's nature. The cosmic microwave background radiation represents the remnant heat from the universe's hot beginning that has cooled dramatically as space expanded over billions of years. This omnipresent radiation bathes the entire universe, but remains invisible to the naked eye because it has cooled to just 2.7 to 25 degrees above absolute zero, making it detectable primarily in the microwave portion of the electromagnetic spectrum. The European Space Agency aptly describes the CMB as the cooled remnant of the first light that could ever travel freely throughout the universe, essentially functioning as a fossil radiation, carrying information about our cosmic past. The existence of this background radiation was theoretically predicted by Ralph Alpher in 1948, in connection with his research on Big Bang nucleosynthesis, conducted with colleagues Robert Herman and George Gamow. However, its actual discovery occurred unexpectedly in 1965 when two radio astronomers at Bell Telephone Laboratories, Arno Penzias and Robert Wilson, detected a mysterious noise in their radio receiver that seemed to emanate uniformly from all directions in the sky. This perplexing signal remained constant regardless of time of day or season, suggesting an extragalactic origin. Simultaneously, a team at Princeton University led by Robert Dick was actively searching for this predicted radiation. And when they learned of the Bell Lab's finding, they immediately recognized it as the cosmic microwave background predicted by Big Bang theory. Both teams published papers in the Astrophysical Journal in 1965, with Penzias and Wilson describing their observations and Dickey's team providing the cosmological interpretation, a discovery that would eventually earn Penzias and Wilson the 1978 Nobel Prize in Physics. The detection of the cosmic microwave background radiation provides compelling evidence supporting the Big Bang theory, which posits that the universe originated approximately 13.8 billion years ago from an extremely hot, dense state and has been expanding and cooling ever since. The standard Big Bang model predicts that the early universe would be filled with intensely hot radiation that would gradually cool as space expanded, exactly matching the observed properties of the CMB. The European Space Agency emphasizes that scientists consider it as an echo or shockwave of the Big Bang, and the Big Bang model is still the only model that is able to convincingly explain the existence of the CMB. The CMB's discovery played a crucial role in distinguishing between competing cosmological models. In 1948, Hermann Bondi, Thomas Gold, and Fred Hoyle had proposed an alternative steady-state theory that attempted to account for the observed expansion of the universe without invoking a beginning in time. This theory suggested that matter is continually created to form new galaxies, maintaining a constant average density throughout infinite time. However, the steady-state theory could not adequately explain the existence and properties of the CMB, which strongly favored the Big Bang model. The CMB's near-perfect black-body spectrum and remarkable uniformity across the sky provided unambiguous support for the notion that our universe did indeed have a hot, dense beginning, effectively resolving the long-standing debate between these cosmological paradigms. The CMB offers a unique observational window into a critical transition point in cosmic history that occurred approximately 380,000 years after the Big Bang. Before this time, the universe was so hot and dense that matter existed primarily as an opaque plasma of free electrons and protons. In this environment, photons could not travel far without interacting with free electrons, making the universe effectively opaque to radiation. As the universe expanded and cooled to approximately 3000 Kelvin, it reached a temperature at which electrons could combine with protons to form neutral hydrogen atoms in a process known as recombination. This transformation fundamentally altered the universe's properties, allowing photons to travel freely through space for the first time, creating what cosmologists call the surface of last scattering. As explained in the search results, in its initial moments, the universe was in an extremely hot, dense state. It was so hot and dense that all matter was in the form of an opaque plasma, and light was not able to travel freely without scattering. As time went on, the universe expanded and cooled until protons and electrons were able to combine to form hydrogen atoms, at which point the universe became transparent, and light was able to travel freely through space. The CMB radiation we detect today consists of these same photons that began their journey at this pivotal moment, though their wavelengths have been stretched by the expanding universe from visible light to microwave radiation. By studying the CMB, scientists can effectively look back in time to examine the conditions of the universe when it was less than 400,000 years old, providing a unique observational test of theories about the universe's earliest moments. While the CMB's existence strongly supports the Big Bang theory, certain properties of this radiation initially presented puzzles that the standard Big Bang model could not readily explain. One significant challenge was the horizon problem, which concerns the remarkable uniformity of the CMB temperature across the entire sky, with variations of less than 0.01 K. This uniformity is perplexing because regions on opposite sides of the observable universe would have been too far apart to have ever been in causal contact according to the standard Big Bang model, meaning they should not have been able to equalize their temperatures. This paradox is clearly articulated in the search results. Astronomers observed that the temperature of the cosmic microwave background, CMB, is nearly smooth and uniform. The temperature can become uniform only if distant regions of the universe can interact and exchange energy. The fastest interactions occur at the speed of light. However, at the time the CMB radiation was given off, two regions that are far apart in space today would have been separated by a greater distance than the radiation could have ever traveled, even moving at the speed of light. To address this conundrum, cosmologists developed cosmic inflation theory, which proposes that the universe underwent an extraordinarily rapid expansion in the first fraction of a second after the Big Bang. According to this theory, shortly after the Big Bang, the universe expanded tremendously in a very short amount of time. This expansion grew the size of the universe from submicroscopic to the size of a golf ball in 10 notes, near 35 seconds. This brief but dramatic expansion explains how regions that are now widely separated were once close enough to establish thermal equilibrium before being pushed far apart by inflation. Inflation theory not only addresses the horizon problem, but also explains another cosmological puzzle known as the flatness problem mentioned in search result. Perhaps the CMB's most profound contribution to modern cosmology lies in its ability to constrain the fundamental parameters that define our universe's composition, geometry, and evolution. The slight temperature variations in the CMB, typically at levels of about 10^5, 1 part in 100,000, contain a wealth of information about the universe's properties. These tiny fluctuations represent quantum variations in the early universe that were amplified by inflation and eventually grew into the large-scale structures we observe today, including galaxy clusters and cosmic voids. Through sophisticated statistical analysis of these temperature fluctuations, scientists can determine essential cosmological parameters with remarkable precision. Research described in the search results employed Bayesian analysis methods to determine what CMB data imply for various cosmological models, including those with different mixtures of baryons, cold C, and possibly hot H, dark matter, vacuum energy L, and curvature energy O in open cosmologies. This analysis revealed crucial insights about our universe, finding that the slope of the initial spectrum is within about 5% of the preferred scale-invariant form when just the CMB data are used, and a non-zero value of OL is strongly preferred, Ca23 for a 13-gyre sequence, similar to the value from SNIA. These findings support a cosmological model where dark energy, represented by L, constitutes approximately 2/3 of the universe's energy density, a conclusion that has profound implications for understanding the universe's ultimate fate. The cosmic microwave background radiation stands as a remarkable testament to the power of observational cosmology. From its accidental discovery in 1965 to today's precision measurements by sophisticated space-based instruments like ESA's Planck mission, the CMB has revolutionized our understanding of the universe's origin, evolution, and structure. By providing direct evidence for the Big Bang theory, helping resolve fundamental cosmological puzzles through inflation theory, and enabling precise determination of cosmological parameters, the CMB has established itself as an indispensable tool in modern cosmology. The CMB continues to drive research at the frontier of cosmological science, with ongoing efforts seeking to detect subtle polarization patterns that might provide evidence for gravitational waves generated during cosmic inflation. As our observational capabilities and analytical techniques advance, the cosmic microwave background will undoubtedly continue to yield new insights into the nature and history of our universe, further refining our cosmic understanding. This ancient radiation, the furthest back in time that any telescope can observe, connects us directly to our cosmic origins and illuminates the path toward a more complete understanding of the universe we inhabit.